You actually know when things need maintaining. You either work on a time schedule basis, but if you're trying to save money and trying to do maintenance smarter, then really what you should be doing is on a predictive condition monitoring basis. And so that requires the use of sensors that actually measure the behaviour of the equipment. Can be vibration sensors, can be pressure, can be strain gauges, can be sound microphone sensors. And so these sensors traditionally are very expensive, but now you can get really quite cheap sensors. And as far as the Internet of Things goes, what you really want to do is to have those sensors embedded in the equipment with its own power supply or battery supply or renewable energy harvesting supply, and then have some means of digitising that signature, whether it's pressure or strain or accelerometer, acceleration, and then to be able to communicate that sensor information to the web, or that's really where the Internet of Things comes in. So I have here an example of a sensor that we put together more than 15 years ago, and this was designed to fit onto large rotating equipment, and it has inbuilt in there a MEMS transducer which measures the acceleration, and also has a thermometer to measure the temperature of the device. So when we developed this, we realised that the concept really would be to embed these into remote machines, and often in places that are not very accessible. So you really don't want to have these battery powered and then every 3 months have to actually replace the batteries. So that brought us into the top research topic of energy harvesting, and there are many different types of energy we can extract from the environment. For example, solar or wind energy. But we've been working, because we're looking at vibration, we've been working on energy harvesting from the vibration environment, and there are different techniques for extracting energy, but we've been looking particularly at the piezoelectric energy harvesting. So I've got an example here of a piezoelectric beam that can be used for that. Here is a miniature piezoelectric beam, and it would be clamped to the machine, and so it's a base excited vibration, and this beam then vibrates back and forwards. So what we find is per metre per second squared, or per G, you can extract, fractions of a milliwatt of energy from these devices if they're operating at resonance. Now, a fraction of a milliwatt might not sound very much, but actually because it's generating power continuously over the days, weeks and months, you accumulate a lot of energy. And so then you can couple that with smart supercapacitors or other recharging devices to recharge batteries and so on, which gives you enough energy, enough power to be able to communicate that information from the sensor, from the smart sensor, to the internet or to the web. So there's a vast array of applications now in industry for these kinds of devices.